Okay, great. Thanks so much, Laura. I'm delighted to be here this morning to give this lecture on interior bulk compositions and the importance of measured masses and connections to atmospheres. So given that the first two talks of this morning focused primarily on rocky planets, in this lecture, I'm going to focus for the most part on planets that are sub-Neptune size and bigger. So planets with extended volatile envelopes. Let's see. Does it advance?
Yeah.
Oh, okay.
It's backwards.
Okay,
Yeah.
Good. So for planets with extended volatile envelopes, where the atmosphere starts, or where the atmosphere stops and the interior starts, is a little bit of a fuzzy question. And indeed, in the literature, there can be a wide range of different potential pressures at that seam. In practice, you might ask, well, why don't we just model the entire planet from the very low pressure exterior down to the very center? In practice, there are different approximations that we make in the various regimes. So for atmosphere models, mostly, but not always, one can simplify things by assuming plane parallel or constant surface gravities, ideal gas equations of state. But those approximations break down as you move into the interior of the planets, where you need to take into account the radial dependencies of surface gravity, mass interior, and also non-ideal equations of state. The flip side is, within the interior models, we are pretty safe in assuming almost everywhere local thermal equilibrium and that the radiation is kind of thermalized, whereas that's not appropriate everywhere in atmospheres. And so in practice, when we try to connect atmosphere and interior models, essentially we want to be careful to check for our transition pressure, essentially that the approximations that we're making on either side of our modeling frameworks, that the approximations don't break down too horribly where we're trying to stitch these models together. Okay, so what are some of the physical processes that connect planet atmospheres and interiors? Well, there are processes both involving kind of energy budgets and also the transport of material and compositions. And so these planets are receiving energy from their host star, of course, but then the atmospheres also get some internal heat flow, some intrinsic heat entering the atmosphere from below, from the interior. And then the planets radiate away to space. So let me dig in a little bit more to this. So here are some example plots from recent models by Paulette et al., showing the connection between atmosphere models and their planet interior models. So here on the left-hand side, we have pressure versus temperature as you go in through the planet, and on the right, radius versus temperature. And these dashed gray curves are their atmosphere models for different choices of kind of a characteristic radii. And this is tied to a specific planet equilibrium temperature, akin to Kepler 138d. But then these colored curves are their interior models, again, for a hydrogen-helium composition, but for different choices of the interior entropy. So the interior entropy kind of sets the deep pressure temperature profile. And you can see here how, to connect the atmosphere model to the deep interior, they need to find situations where both the radius, temperature, pressure, and also the upwelling radiative energy fluxes match at the seam. And they've highlighted their best match here in these plots with the bolded curves. Okay, so then this is for a particular snapshot. Then the atmosphere generally radiates a bit more radiation to space than it's receiving from the host star. And that leads the planet to cool and contract, essentially with the little bit of extra radiation coming from the interior. And so the atmosphere and interior evolve in tandem. Here's an example of some evolution calculations that have connected an atmosphere model to the interior. And here on these plots, the vertical scale on a log scale is the intrinsic luminosity of the planet. So that's the little bit extra that the planet is radiating away to space in addition to what it's receiving from the sun. And then time is on the horizontal axis, again on a log scale. And on this leftmost plot, this is a case tuned to match Jupiter, so a massive gas giant. And on the right-hand side, we have Neptune. And in these curves, the dashed red is showing the total intrinsic luminosity of the planet as a function of time based on these evolution calculations, coupling the atmosphere and interior. But then these other colored curves show the different contributions to that intrinsic luminosity. So the two different shades of blue are contributions from the envelope, be it contraction or cooling. But then the dotted, I guess this is kind of a deep brown or deep red and deep green, are contributions from the core. And so as you can see, for the smaller Neptune-like planets, the core cooling and contraction make a dominant contribution to the intrinsic luminosity. Whereas for these massive gas giants, it's the envelope. Now, this is for kind of specific cases where you have a core and then a homogeneous envelope on top. The actual breakdown and the thermal evolution of planets can be rather sensitive to the detailed interior structure, whether there are composition gradients or thermal boundary layers. And so that's just a caveat to keep in mind here with these plots. Okay. So those were some examples for solar system planets. Here's just an array from the same paper of coupled evolution calculations of the atmosphere and interior for a range of exoplanets with a variety of masses. So each color here in these plots corresponds to a different mass, and the core mass of these planets increase in tandem with the mass, kind of tuned to match the observed populations of planets. And here again, they're showing time on the horizontal axis, and we have radius on this bottom right plot, the effective temperature of the planet, bottom left, the intrinsic luminosity, kind of like I was showing before on the previous slide, up here on the top left, and the entropy, or kind of a measure of the deep pressure temperature profiles of the planets here on the vertical. And the main thing I want you to take away from this plot is that these different line styles essentially are for their different choices of atmosphere model grids that they've connected to the deep interior. So they're considering a couple different metallicities, solar metallicity and slightly metal enhanced, along with cases with and without clouds. And even for this relatively narrow range of scenarios, the choice of atmosphere model does affect the cooling of the planet and these evolution tracks. And so kind of the span or the spread of all these different curves of a different color kind of gives you an illustration of the extent to which varying the metallicity or including clouds or not affects the cooling of these planets. Okay, so I've talked a bit about the connection between planet interiors and atmospheres in terms of energy budgets and evolution. Now let's talk a little bit about the connection in terms of compositions. And so I think on day one, Julian Moses spoke about thermochemical equilibrium and quenching, and that applies here too. So here's a schematic from a recent paper by Yu et al., where here are showing kind of an example chemical network in a sub-Neptune planet, where as you go deeper into the planet, as you go down in this plot, and so towards higher pressures and temperatures, you have thermochemical recycling. The species are in their thermochemically preferred configurations. But then as the transport timescales become shorter than the reaction timescales, they can be quenched. And then as you get into the upper atmosphere, photochemistry becomes important. And so in this paper, Yu et al. Pointed out how for sub-Neptune planets, this can give us a potential avenue to identify the presence of a surface in the planet. So if a planet has a shallow surface, essentially it is cutting off this possibility of thermochemical recycling, and that can affect the abundances in the upper atmosphere. And so here they're coloring blue the species that they find to have decreased in abundances when there's a presence of a surface, and in red the species where they see an increase in the abundances compared to the no surface case. Okay, so this is kind of this transporting and quenching part of this cartoon. Now let me briefly mention kind of partitioning and rainout. So a familiar example of this from our solar system is helium rain in Jupiter and Saturn. And here's a schematic from a paper by Wilson and Militzer tied to Jupiter. And so within the interior of Jupiter, hydrogen and helium become immiscible, and helium is actually raining towards the center of the planet. And it turns out, based on the ab initio calculations performed by these authors, that neon prefers to partition into the higher density helium-rich condensates in the atmosphere. And so the neon rains along with the helium towards the center of the planet. And this can explain the 10 times decreased abundance relative to solar of neon that's been observed in Jupiter's atmosphere. So phase separations and partitioning of trace species between different phases can affect the relationship between the composition of the atmosphere of a planet and the composition of the deeper layers. One example of this for temperate sub-Neptune exoplanets is shown here, and this is taken by from a paper by Renyu Hu and collaborators. So here they're considering temperate sub-Neptune planets, and on the left they're showing the cases of for planets with kind of massive hydrogen dominated atmospheres that are sufficiently massive that they extend to high enough pressures and temperatures to get the thermochemical recycling. Whereas on the right-hand side, they're showing the case for planets that, temperate planets that have liquid water oceans. And so this kind of sets a surface, as we saw from the Yu et al. Paper, but also Hu and collaborators found that ammonia would be even further depleted because it likes to dissolve in the liquid water oceans. And so they predict that for temperate sub-Neptunes that don't have liquid water oceans, methane and ammonia would be the dominant carbon and nitrogen carriers, whereas in cases with liquid water oceans shrouded by a smaller hydrogen-dominated atmosphere, carbon dioxide and nitrogen would be the dominant carriers. Okay, so now let me just briefly talk a little bit about, after kind of hanging out in theory land, I will dip my toe ever so slightly in the connection to observations and talking about how we, what information we can get from combining observations of atmospheres with measured mass and radius measurements when interpreting planet compositions. And so perhaps one of the more famous planets was the first sub-Neptune planet ever discovered in transit, first volatile rich sub-Neptune sized planet. And it already gave us a bit of a preview of some of the challenges we would face in interpreting planet compositions with measured mass and radius measurements. So with a mass and radius measurement alone, there's a wide range of potential planet bulk compositions that can match, especially in the sub-Neptune size range. And this kind of boils down to the fact that the density of water or other volatile ices is intermediate to the density between hydrogen and helium and rocky material. So you can almost always find some mixture of hydrogen, helium, and rock to mimic the density of water. And that leads to a large uncertainty in the water mass fractions of planets in the sub-Neptune size range. Now, we could hope, and our distinguished session chair, Laura Kreidberg, of course, made valiant efforts to try to measure the mean molecular weight of the atmosphere with transmission spectroscopy. And with Hubble and atmospheric transmission, of course, we were foiled a bit by high-level aerosols and hazes. But now with James Webb and emission and phase curves, we're starting to see evidence that this planet has a metal-enriched atmosphere, more than 100 times solar, in addition to reflected high-level aerosols. And so I'm really excited to see what we'll find with further characterization with James Webb, and enabling us to use atmosphere models essentially to set an outer boundary condition on the compositions of these planets. Now, the flow of information doesn't just go from atmospheres to bulk compositions, but can also go in the other direction. So, and here's an example of this from a paper by Thorngren and Fortney. So here I'll show an example for the hot Jupiter WASP-43b. And these authors essentially fit the measured mass and radius and equilibrium temperature with a rough constraint on the age to interior structure models for this hot Jupiter. And so by fitting the measured mass and radius to these mass radius relationships, they're able to retrieve a constraint on the total bulk metallicity of the planet. And here's some examples of the posteriors that they obtain. So the first column shows planet mass. The next column shows this Z sub P is the total bulk metallicity of the planet. So in this case, they have taken a homogeneous model extreme where the entire planet has the same kind of metallicity. There's no condensed core. And in that case, they're able to get this kind of limit on the total metallicity of the planet. The additional heating efficiency, which is tied to inflation and the age. And so in this case, the bulk metallicity of the planet retrieved from fitting the mass and radius actually provides an upper limit on the expected atmospheric metallicity. So the metallicity of the planet can't increase as you go out to the atmosphere. Otherwise, it could be, you could get an unstable density distribution. And so in this case, they're able to place an upper limit on the atmospheric metallicity that could potentially inform any atmospheric retrievals, which could be helpful, especially in cases where clouds introduce additional degeneracies. Okay, so in the last few minutes, I wanted to turn to the other topic I was assigned, which is why the importance of mass measurements. And so mass measurements are important for characterizing atmospheres for multiple reasons: to constrain compositions, to assess the planet's thermal evolution, to constrain the surface gravity and atmospheric mass loss rates, and to understand the broader context. And so I'll just briefly give a bit more details on each of these points. And so I just spoke a bit about attempts to constrain planet bulk compositions with measured mass and radius measurements. I just wanted to highlight an exciting recent development where Caroline Paulet and collaborators with detailed measurements of the mass of Kepler-138d with transit timing variations and radial velocity observations, they're able to place pretty stringent constraints on the composition of the planet and showing that it must be volatile rich, but also that a pure hydrogen dominated atmosphere is disfavored due to atmospheric escape. And so this is a case where the interpretation of the measured mass and radius kind of gives us some insights into what we might expect with further characterization of this planet's atmosphere. Now, once you've actually gone and measured a transmission spectrum of the planet atmosphere, having measured the mass of the planet is very helpful in the retrievals. And here I'm highlighting plots from one of my fellow speakers in this session, kind of showing for this now simulated spectrum of TRAPPIST-1e with a simulated stacking of 5 transits from JWST, kind of how much better you can do in retrieving the temperature or the water mixing ratio in the atmosphere of the planet when you have a mass measurement. And this is especially true, as Natasha showed, for small planets. Okay, in the interest of time, I'll skip, but say this also holds up, perhaps even more so, looking even further ahead to characterizing planets in reflected light. It's challenging to retrieve a surface gravity from a reflected light spectrum. So you'd really want an independent measurement of the mass. Now this is the cosmic shoreline, which was foreshadowed in an earlier talk this morning. And indeed, another reason why mass measurements are important is because they give us some indication or way to assess atmospheric mass loss rates. So here, the cosmic shoreline, we have the insolation of the planet received relative to Earth on the vertical axis and the planet escape velocity on the horizontal axis. And as you're likely familiar, the planet escape velocity is tied to the planet mass. It's essentially a measure of the gravitational potential energy needed to remove material from the planet's atmosphere. And so this cosmic shoreline essentially is a dividing line between the planets empirically that are able to retain an atmosphere, shown by these solid dots here on the lower right-hand side of the planet, of the plot, compared to planetary bodies that don't manage to retain a significant atmosphere, shown with the open circles. And so by measuring a planet's mass, you kind of get a measure of the escape speed, and you can have some indication of where you fall on this relative to the cosmic shoreline. Okay, and so far, I've mostly just been talking about one planet at a time, but of course, planets aren't all alone. They're often found in planetary systems, and measuring the masses of the planets is important to get that system-wide context, to understand the interactions with other planets in the system, the potential delivery of volatiles that could contribute to the atmosphere from planetesimals, and gravitational interactions. And finally, mass is a fundamental property of any astrophysical body. And so for me, from a more philosophical standpoint, I kind of, if we don't know a planet's mass, can we really say we know the planet? And so I will stop there and just sum up. So in this lecture, I gave a bit of an overview of some physical processes that connect planet interiors and atmospheres. I gave a little examples of how combining insights from planet atmosphere observations and mass radius measurements can inform and give insights into each other and the retrievals, and also briefly summarized a checklist of reasons for why mass measurements are important. So thank you so much for your attention.
Hi, thank you for that awesome talk. I was wondering, are there any other sort of axes of constraints that we can think about for trying to infer the structure of interior compositions, like say stellar abundances or something like that?
Yes, certainly. And that's actually an ongoing area of research to try to understand, I would say from an empirical standpoint, how stellar abundances imprint themselves on the abundances in the planet. We can, as modelers and theoreticians, we can always make constraining assumptions. But I'm most excited about, as we continue to characterize, especially small planet densities, understanding the, from an empirical standpoint, the correlations between stellar abundances and planet compositions. So.
Nice talk. Question is that we're finding a lot of planets that have surprisingly lower densities than we expect, given our bulk metallicity models. And I was wondering if you had any thoughts about what maybe in their interior or in their atmospheres or something that we're missing in our models that could suggest how these planets are maintaining a low density.
So sorry, I didn't quite catch the first sentence. So you're saying we're finding more planets with low densities?
Surprisingly low densities, and not just like the inflated hot Jupiters, just in general, where they like say the super puffs or even some gas giants that have densities of 0.3, 0.4 grams per cubic centimeter, which can't be explained by like the Thorngren models. And so I was just wondering if you had any thoughts about what are we missing that could inflate their radii?
That's a great question. We should maybe take that kind of offline because I think that could be a big discussion. But also, I think Peter Gao, who's a speaker later today, I believe, has published some hypotheses on this. And there's been some recent papers talking about rings as a potential alternative explanation for super puffs. So yeah, they're a puzzle, and theorists love a puzzle.
All right, well, on that note, let's thank Leslie and all of our team.